much. It's a pleasure to be here. It's a pleasure to be in beautiful Stockholm, and I'm glad to have the opportunity. I am Mike Toecker. I am not M. Tucker Zinn, though I do like Mr. Zinn very much. I enjoy his presentations, just at M. Tucker. I'm a professional engineer out of the United States. I've been doing industrial control systems work for about 10 years now, primarily power generation, but I've also done some work in mines. I've done some work in chemical facilities, gas, things like that. I've worked with just about most of the big iron out there in the power industry. So I'm also this guy. So I'm here to talk today about maintenance and test equipment. Now, I promise this isn't going to be a 101. I know right now that we're in a room full of individuals who know control systems, all right? But I'm not sure we're in a room of individuals who know the maintenance of their plants, of their facilities, all right? And so maintenance and test equipment is basically it's a class of industrial equipment that's used to maintain and test, all right, to ensure that the system is working appropriately. And it's not the cyber system at all, it's the electrical and mechanical systems. And we use this in order to ensure that our electrical and mechanical systems are in appropriate condition before we go and run them. All right, if you go and run a bad pump, well, you're going to have a bad time. It's going to break, it's going to cause nasty things to happen, it might even pollute your water. All right, all of these things are things that engineers, we try to hold all of our variables as close as we can. We try to eliminate whatever ones we can when we're doing this type of work. So it's on-site reliability engineering is the basic idea. So basically, MNTE is equipment used to maintain and test other equipment. All right, so quick example, you've probably seen MNTE if you have a car. All right, we kind of know this picture. All right, this is an illustration of a car with all of its various control systems and basically electrical and mechanical systems shown up. So you've probably seen this. What you probably haven't thought about, unless you, every once in a while, you take off your driver hat and put on your maintenance hat, is all the stuff that we do to make sure that it's in good working order. So we do things like battery testing. We do things like alignment. We have emissions compliance. All right, we have computerized balancing of our tires. What happens if you have unbalanced tires? Your road noise increases. All right, your wear on your tire increases. You end up spending more money sooner than you expected. And you may even have a failure at some point. So, and then of course you have your engine diagnostics, your EODB, here in Europe, your OBD port, in the US, the OBD2 port, which allows digital access to your control systems. And you use that to pull trouble codes. So I've had a run-in with MNTE I didn't like. I went to the garage, I went to just get my oil changed, and they did a full inspection of my car, which by the way is a Volkswagen Jetta. Love my Volkswagen Jetta. It's not a diesel, that's why I love it. So, well, at any rate, okay, I get this wonderful, wonderful call about halfway through my workday, you know, where I'm just like, oh, I'm just getting an oil change and my tires rotated. Well, yeah, Mr. Tucker, we ran a automated test on your alternator. It's going bad. You're gonna have to replace it. And I said, excuse me, where am I buying this alternator from? You? So you want me to buy an alternator from you so we can install it and I can pay you to install it? I don't know about that. And he said, well, we ran it through our automated system. It says it fails. Well, I ended up paying $500 for a new alternator because a computer told me so. A computer said, replace your alternator, Mike. And now I'm $500 poor. I could have done a lot of stuff with that money. Although I'm sure it was a bad alternator, but you know, it got me thinking, maybe it wasn't a bad alternator. Maybe they just like selling alternators that they don't need to and then repackaging them and putting them back in. I don't know. But that's the whole reason for the automated test was that originally it was just the mechanic's word. He would look at it, he would evaluate it, and he'd say, look, I think you need to replace this. And you go, no, I'm not doing that because I don't trust you. Well, that's why the automated system's there to help. You know, I mean, nobody cheats on tests, right? No. Nobody cheats on tests. Well, I'm going to tell you this right now. Industrial facilities only differ in the scale of what's going on. I had a $500 expense for an alternator, all right? An industrial facility might have a $500,000 expense for a motor or a similar system. Well, they've got at least 2 orders of magnitude more systems in an industrial facility than I've got in my car. All right, think about that for a sec. They do 100 times more tests on their facilities, equipment within their facilities, than you do on your car every year. It ain't just an oil change for them. And a lot of this is really important stuff, safety-related stuff. Things like, you know, for the car side of it, it would be brakes. For the other side of it, it's safety-related valves, things that need to operate when bad things happen. And we test them to make sure that we're confident that they can. All right, so a little bit of honesty here. I'm unaware of any incidents where hacked MNTE has caused an issue at a plant. So ICS compared to MNTE, we're familiar with ICS. It's operational. We talk to operators a lot. We say, hey, how do you run your process? What do you need to run your process? Show me where you get your data from. And then they all point to the control system, and you go, that's totally hackable. Well, on all of the ICS there is, in general, it's networked in some manner. Maybe it's not TCP/IP, maybe it's something else. And it's for monitoring the process in real time. They want real-time knowledge of all the variables in the process so that they can make appropriate decisions on the health of that process and on maintaining that process. So, but M&T is different. It's maintenance focus. You're not talking to operators, all right? You're not talking to guys in chairs, all right? You're talking to guys with hard hats and with gloves, all right, and who have to worry about lockout, tagout procedures in the field, all right? It's a maintenance piece. They're rarely networked, rarely. You'll see some of it networked. This is new. This is new to them, all right? And it will be networked with TCP/IP most likely. And then you evaluate specific criteria associated with the process equipment. So they're not at a very broad level of the process, they're at a very specific level. They want to know the conditions that are actually making their pump work, the conditions that are making their valve work, the conditions that keep the motor running. And it's mobile, all right? You don't get to take something into the shop when it's installed into the plant. You get to take the test equipment out to it. Now, in MNTE, we have a trend towards digital equipment. All right, we used to use analog stuff, RLC circuits and capacitors and diodes and things like this with little gauges that would bounce, and you had to interpret those results. Well, now there's a trend towards digital, all right? And what you see is some of the old guard stuff on the left. Is that on the left? Oh, excuse me, I'm looking at the wrong slide, aren't I? Okay, there's a trend towards digital equipment. That's my bad, folks. I'm sure you're very confused. There's a trend towards digital equipment. So on the left-hand side is a Sanwa. All right, that's an old analog system. It's got a needle. It bounces whenever it sees something. You don't get to record data on that. You get to analyze it. You get to view it, and you get to interpret it. Digital equipment like a Fluke, you can actually record data. You can take a look and see, okay, what was the exact response? You can also run mathematical functions on things in order to figure out what it's up to. So there's a trend in digital that parallels the trend in digital for control systems. And because of this, well, guess what? We get the usual digital vulnerabilities along with it. All right, as they've started to build these pieces of equipment, they've used common off-the-shelf stuff, like operating systems. I've seen more Windows XP in this stuff than I would care to admit. I've also seen Windows CE. I've seen Windows 2000. All right, we have newer stuff coming out that's running BusyBox Linux. I'm a happy guy there, but it sure is got a little bit, there are a lot more people out there with BusyBox Linux security experience than there were of the old Palm OS stuff. So on the left, right here, I actually own several HART calibrators. Raise your hand if you know what HART is. Anybody? Okay, great. I love talking to experts. All right, this right here, a HART calibrator, we're used to the HART on the actual control system. Well, there's actually a handheld device that you can hook up to the HART bus and do all your work that way. Well, that's a DLL from a heart device right there that I pulled out of one that I own. All right, that's the actual DLL that handles heart communication. There are 36 more DLLs and applications on this thing, all of them visible through common tools. So once again, the vulnerability's there. That's basically what I'm trying to say, is that the digital vulnerability's there. We're using these, we're now using common off-the-shelf stuff in order to do our work with. Second, it's bring your own device industrial edition. So imagine for a moment, okay, that you were going to go change the oil on your car, but in order to change the oil on your car, you had to pay $60,000 for a piece of equipment that would do it for you. Better way to put that would be like an automatic alignment machine. So if you want to do your alignment right, you need an automatic alignment machine. Those cost $60,000. You're not going to buy one yourself and put it in your garage. That's a waste of money. All right, not unless you actually do alignment for a living. No, you're going to take it to the mechanic. It's the same deal for MNTE. All right, this equipment costs a lot of money. And therefore, it's in the hands of guys who use it day after day after day after day. They go from site to site to site. They do tests all day, every day, and then move on to the next site. All right, that includes digital stuff too. So hooking up a heart calibrator in one plant and dragging it on to the next and doing the exact same work again. Or motor testing, or valve testing. It's the same deal. So right here, what I've got here is a RFP. I pulled this off of the internet. I'm sure somebody's going to get angry at me about this. This is actually an RFP for substation testing. So if you've ever been in a substation, you know that they got a lot of equipment there. This is actually for substation testing. So if you can see right here, testing organization shall provide field technical services, tooling, equipment, instrumentation, and technical supervision. It's all in one, baby. Come do all my testing for me. You may not run into an owner that knows how this works. They just spec it out. They want a written record of all tests and a final report. Well, guess what? The wonderful thing about this automated MNTE, it generates its own reports, and you can print it out on a printer. And if you want, you can upload it to the web directly from some of these. It's wonderful. The testing organization shall be an independent third-party entity which can function as an unbiased testing authority. All right, this is going back to the mechanic. The mechanic I don't trust because he's selling me a new alternator while telling me I need one. All right? I don't trust people that say you need to buy my stuff because your stuff is failing. This demonstrates that concern right here on an independent testing authority. These guys are not allowed to sell equipment that they say is bad. That's a good thing. And so how do you think they're upgrading the firmware in this relay? Well, that means that the testing is, look up to the top. All equipment must be provided. All equipment, i.e. they're going to provide a laptop themselves to do the firmware update on all of your relays. Okay, that doesn't seem like a good idea. That seems like something you should probably handle. But anyway, what are the consequences of malicious MNTE? Well, ICS, it's pretty much immediate. It'll shut down the process, or it'll cause some issues, or you'll get bad quality out, or something like that, but it's immediate when you have your ICS compromised. It's got a direct effect on the process, all right? The process is the target, all right? Whether you're making chemicals, gas, power, whatever. On the MNTE side, though, it's attrition. It's death by 1,000 cuts. It depends on how many of these systems you have in your plant, because it's not going to cause an immediate impact. This is something that indirectly affects the process. It's failure of equipment or having to rip equipment out and pay money to do so when it was actually good equipment. It's lowered efficiency, which then translates into higher costs. All right, that's the issue that you end up with MNTE. It's a different threat. All right, it's a different kind of target. So, some examples of MNTE. Yes, I got all that. Digital to digital connections. These things scare the crap out of me. What you're looking at down in the lower left-hand corner is the evolution of heart calibrators. From a Rosemont 268 all the way up to an Emerson who bought Rosemont 475. Highly digital. Everything's got firmware in it. Interacts directly with heart devices. You can change things, you can stroke things, you can make it do anything you want. On the right-hand side, this is actually a setup for a bench cal using a heart calibrator. This is what's known as a documenting process calibrator by Fluke. this touches plant equipment. Now imagine this particular pressure transducer installed in the plant. All right, that's how this is generally done. So these are some of the most interesting from a pure cybersecurity perspective. All right, these are interacting via digital protocols to other digital systems in the plant that may or may not be monitored and may not even be capable of traditional monitoring, such as what Chris and Rob were talking about. So these right here, this is an area I'm going to be investigating a lot over the next 2 years, because a lot of this stuff gets firmware updates direct from the internet. A lot of it gets device descriptors direct from the internet and is downloaded over plain Jane HTTP. No S for us. Thanks, guys. Next up, motor condition evaluation. So this is actually 2 sets of automated motor condition evaluation test sets. All right, these will give you a pass or fail on a motor, similar to my alternator. All right, the picture on the left, this is actually from a biodiesel facility. These motors drive pumps that drive, I'm not exactly sure what they drive, actually. I'm assuming it's something flammable. Maybe, maybe not. All I know is that if they break down, certain parts of the plant are going to go down. They break down too, you're going to go into an outage on that, you have to replace it. So these particular motor condition evaluation, you hook them up, press a button, and off you go. And it gives you a condition at the end. Next up, valve testing. All right, valves kind of keep water from going to certain places, they keep gas from going to certain places, they separate fluids, they move fluids, they stop fluids. That's a big deal, stopping a fluid when you don't want it to go somewhere. And in order for them to do that, they have to turn. And that turn requires a positioner, which requires a motor, which requires, you get where I'm going here. We have to test and make sure that these valves can actually work when they're supposed to. This is done with an automated valve testing system. This is one right here. It's laptop driven. Probably runs Windows XP or Windows 7. Does it connect to the network? Well, you got to print the report somewhere, right? You got to get it off via USB, right? So the more interesting part of this is that they are actually starting to cross old style valve testing with new HART smart positioners, which means that you can now use the HART positioner as part of your test, which means your system's now hooking up via HART, the same way those HART calibrators did on potentially a very important valve. Oh, if you were in electric power and you thought you were getting out of this, you're wrong. Substations. Relay testing and validation. This is required by many regulations, is that you have to ensure that your relays are going to work under the conditions that you said that they were going to work under. All right? Millions of dollars have been spent developing relay test programs. They use automated test equipment like this. Automated test equipment that has updatable firmware, that may be running on a laptop, that might interact directly with your system over 61850. That sounds like a lot of fun. So, transmission, not immune. And here's another fun one. I love this particular set of things. This is the epitome of maintenance and test equipment. You can't see inside a pipe while there's a fluid in it. So you have no idea if there are any problems with the pipe inside. You don't know if any cracks are developing, anything like some tech may have dropped a wrench on it and cracked something. You don't know if certain bits and pieces aren't working. But what you can do is you can run a probe either on the outside or on the inside. This particular one is on the inside. And it will actually show cracks, it'll show deformations, it'll show deposits of magnetite and other interesting fluids as changes in that graph. So this is probably be a better graph for you to take a look at once we post the slides online. But the idea is that wherever there's a deformation or some kind of change, you see a line. That's the idea there. And once again, this is digital equipment. Some of it's laptop driven, I just don't have a picture in there. So what might an MNTE hack look like? As an apology to my sponsors, I had to pull an entire section of this. I was originally going to do it on safety-related valves. Yeah, that sharp intake of breath from somebody that was next to you, they're probably very happy right now that I didn't put that in. So we're actually going to talk about motor hacking. All right, the motor test hacking. So the idea is that motors are a major component of any industrial facility. All right, they cost a lot of money. I actually threw in some list prices here. A 500 horsepower motor, yeah, that's going to run you around $80,000. And that's just to replace the motor. That doesn't tell you the cost of design. It doesn't tell you the cost of the outage. It doesn't tell you the cost of bringing other equipment down. It doesn't tell you the cost of personnel. It doesn't tell you the cost of, oh my God, yeah, we have to test this thing again, don't we? So all of this has to be covered when a motor goes down. Hence, we test motors to see where they are in their useful life. So, motor test. Most motor failures on the electrical side come from insulation within the motor going bad. All right, it's a hot environment. There's a lot of stuff going on there that's at the very edge of what we understand as far as electricity goes. Insulation will expand. The internal windings will expand more. They go in, they go out, they go in, they go out. Okay, anybody who's tried to bend a hanger in half knows what's happening here. All right, eventually the insulation and the windings are going to find a way to fail. So the short may not appear until a certain voltage threshold hits. So in other words, you're applying a voltage to this motor and you kick it up, boom, 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 in steps. And the idea is that eventually you're going to reach, if the motor's bad, you're going to eventually reach a criteria where it's going to change, where there's going to be a spark, and that spark will then happen at lower and lower voltages as you go along. So let's see here. The surge testing process. So the way that it works is you charge up a capacitor to a voltage set point. Now I included this graph here. The voltage set points on this one are 500, a little over 1,000, and 2,000. So you're charging it up to a certain voltage. You then discharge that capacitor. Boom, you send an impulse through the motor. The charge dissipates. It produces that characteristic waveform that you see there. It's a different characteristic waveform for each motor. It depends on the winding, it depends on what it's doing, it depends on a lot of stuff. All right. You record that waveform and any other associated data. You compare that current waveform to the previous waveform using certain mathematical methods. And then you increase the voltage and do it again. And you continue doing this up to a certain limit. And the automated test system will record all of these particular pieces while it goes through. So that's kind of that's the really, technical explanation of it. I like the fun explanation. Basically, we're hitting a punch me clown over and over and over again until you hit it so hard that it goes bouncing across the floor. It does something different. So rather than going down and coming up, down and coming up, eventually the kid's going to hit it so hard that it's going to go skittering across the floor and he's got to grab it and work on it. That's a bad motor. That's a bad motor. So, he's doing the same thing. And you hit him harder, and well, yeah, he pulls out a gun. That's a dead motor. Yeah, I like that explanation better. All right, so back to graphs now that I got you laughing again. All right, failure criteria number one when you're doing this kind of test is if one of your waveforms, basically you have a waveform that you're using as your reference, that's the previous waveform, and you have the new waveform, all right, which is the one that you just did. If at any point you see a shift to the left in the frequency of it, all right, that means that it's more than likely a bad motor. All right, in mathematical terms, your crossing of 0 is different between the two waveforms. They should be almost exact if you've got a good motor, regardless of the amount of voltage you put in. Failure criteria number 2, if the changes between each one of your pulses result in a different shape of a waveform, so i.e. the 0 crossing is the same, but something else is going on. Now here's the funny thing about it. This is a fail. This fails. This is a bad motor. Can you see a difference in this waveform shape? Because it looks tiny to me, and I know it's failing. The reason, now the way that we figure out it's failing is we use a PPEAR. It's an error area ratio. This was developed by a company that's going to be very angry at me at some point for bringing this up. What it does, it's a mathematical formula that basically says this is the difference on the characteristic wave. This piece down here, where you see that little red line go up, that's actually the graph of every single test. Oh, where's my time, by the way? How am I doing? Okay. I think I'm going a little bit longer than I usually do, or that I thought I was going to. So anyway, the mathematical formula has just told you that this is a bad motor. Sound familiar? You're about to spend $500. So that's the dotted line. So it shows a significant deviation from the previous. Now they're supposed to look exactly alike. All right, think of bowls stacked on top of one another. Yes, you're going to stack them higher each time, but they're still bowls. Or you can always just say, why does this work this way? Anybody a big fan of Super Nintendo? I love the Super Nintendo. I play F-Zero all the time on the airplane. I was really grumpy because I forgot my controller this time around. But one of the best ways to kind of describe this is that yellow line is the start line. All right, in F-Zero, it's a racing game. And so you take off from the start line and you zip around the track. All right, and your lap time is going to be generally the same every single time you do it. Well, it would be if it weren't for the fact that F-Zero gives you these power-ups that allow you to get super speed every once in a while. And so if you think of the racetrack as the motor winding, all right, and you think of this area around C and D, this circled area here, as a short circuit, well, that first lap you do at a low speed, you're going to be fine. But you know what? You don't want to go at low speed. You want to get the best lap time possible. So you're going to use that power-up the next time you go around, i.e. you're going to increase your voltage. And you know what? You're going to use that blue bar as a jump, and you're going to skip an entire section of the track. All right, that's why this works. Now all of a sudden your lap times are significantly different, and you have a bad motor. All right, so I'm going to discuss the process to fake a signal. I'm not actually going to throw up any math because I'm not quite complete on everything that I have to do, but we covered a couple of basic things. So we have a characteristic wave. That characteristic wave is going to look generally the same with differences in amplitude, i.e. it's going to get wider from top to bottom as we go through. Mathematically, the idea is that we want to replicate that standing wave whenever we want to create a false signal. So the idea is that you take your previous one that was good and you expand on it. You extract the noise from your test signal, all right, similar to the way that Jason Larson discusses it in his triangles presentation. And then you create a standing wave that is slightly larger within your EAR range that you've set, so 4 to 5%. All right, and then you apply the noise to that signal that it's a smooth wave at that point, but you apply then that noise that you pulled from your test, and now it looks like an appropriate one. I'm not a math major, and I'm looking into how to do this, but the idea is that you fake the signal by building a characteristic wave based upon the previous one. You don't try to do some fancy math and generate your own. So what are the consequences of a bad motor? Well, you have two potential consequences when it comes to malicious MNTE, okay? You're going to have a bad motor reporting as a good motor, all right, which means you're going to leave it in. Failure of the motor is a given at some point. Once it fails that test, it's going to die at some point. You need an engineer to actually look at it and see how far into the process, how much more life it is. All right, that test triggers a whole series of evaluations at that point. You're not going to have any maintenance activity to open it up. You're not going to catch it, all right, because you're not going to do a physical inspection because your test was good. I say here it's impossible. I've found out that it's not impossible. You can make reasonable estimates based on how long you've been running it, how many hours are on the motor, things like that. I had a couple engineers tell me, yeah, I can generally figure out how much life is left. So just ignore that impossible to determine part. And then the impact of the failure depends on what the motor's doing. You know, if the motor's running your go-kart, well, you know, it's going to stop. If that motor's running, you know, a pump, well, that pump's going to stop. What's that pump doing? A good motor reports as bad. Basically, when you have a good motor and it reports as bad, the engineering's going to take a look at it and they're going to go, huh, this is odd. I don't know why it's doing this. We better pull it out, but we're going to want to send it away. Motor will get removed. Money will be spent to order, design, install, and test. And it's possible that the motor will be sent for third-party testing. Well, if you're an attacker, you want to minimize your discovery risk. Okay, so if you have a bad motor reporting as good, that's what that's what they're going to send out for test. If you have a good motor reporting as bad, that's what they're going to send out for test. Which one of these things is most likely going to end up with you getting discovered? It's really tough to test molten slag to see if it's actually a good motor. So I'd be a really poor industrial security consultant if I didn't give you some mitigations, or at least some idea of, hey, we may have a vulnerability here, we need to evaluate it. So step one is you want to identify your high consequence equipment. Big stuff, expensive stuff, stuff that can cost human lives, stuff that has a regulatory impact for certain industries. I'm thinking FDA and a couple others in the United States. So you want to identify your high consequence equipment. The funny thing is that generally you already know this. If you're running an industrial facility, you know what stuff is really expensive, you know which stuff will kill people. So this list should be readily available. Step two is you want to identify the tests that are done on your high consequence equipment. You're not going to be talking to the same people that you normally talk to. Mostly, a lot of us talk to the head INC engineer or a network engineer or an operator or something like that when we want to get information on the process. You're going to be talking to somebody in charge of maintenance at this point, because that person is the only one who's going to know what tests are being run on your high consequence equipment. Thirdly, you want to evaluate the susceptibility to malicious cyber influence. And wow, that's an open-ended question right there, isn't it? Basically, you want to look at each test and you want to see, all right, what could be done to potentially impact the validity of the test? Is it just an automated system that does this? Do I get a plain old pass-fail and then I go off on my own, or is there some sort of second check going on? You want to evaluate its susceptibility and rate it on a scale. Highly susceptible stuff used on high consequence equipment should be protected. And you want to identify and apply protective measures at that point. There's not a whole heck of a lot you can do for some of this stuff, especially since third-party vendors bring it in. Do what you can. And this is where creativity is going to come in, because a lot of this is not immediately obvious. And this is not something that we've really secured before. And I'm actually thinking bring your own device policies might provide a decent mechanism for securing some of these things, because they're of a similar nature at that time. So, all right. Any questions?
Oh, thank you. Yeah, that doesn't really look like a smart idea. No, doesn't look good.
No, that's not very bright.
So the audience have got a question. Do your organization consider the impact of maintenance and test equipment? It seems like, yeah, fair enough.
Well, do they consider the cybersecurity piece of it? I think every plant out there knows that they have to do maintenance and testing.
Yeah.
I think every plant out there knows that that has to be done appropriately, that they need to have a program for it. But I'm not sure they've considered the potential consequences of malicious influence. And it's malicious influence, too, that's outside of the people who are doing the test. They may not have any idea that the equipment that they're using is potentially compromised. I've actually run into times on the web, all right, where individuals using this equipment are posting on the web saying, help me, I've got a virus on my laptop. And that laptop shows, like, the specific test equipment that I've got in this presentation. So I'm not sure, I'm not sure I believe that. Forgive me.
No, but I think you're right. I mean, testing and maintenance in this area is something different, maybe.
It's new. It's something
but you know,
nobody's really looked
your
at.
presentation gives me the creeps. Who should we trust?
Who should we trust?
Yeah.
We have to figure that out. We have to determine what level of risk we find acceptable. We need to figure out if there's actually a threat here. This is not something that we've really looked at before. And to be honest, maybe a lot of industries don't need to look at it. But I think a lot of industries do, especially since we're bringing in equipment from outside vendors who may not have the same commitment to cybersecurity that an organization may have.
So we have a question here. The challenge for industry is we need to vet the supply chain on vendors' equipment. How do we start?
Oh.
Oh.
How do we vet this? Okay,
I
need
think
to see
so.
it again. Because we need to vet the supply chain on vendors' equipment. How do we start? See,
you have a fan club too, you say?
Toecker, yeah, that's